Hello, and thank you for attending our talk on CoCoNUT. Structural code understanding does not fall out of a tree. First, let us get into the motivation of our study. Large language models have been shown to be very effective at basic code generation tasks, recently saturating benchmarks like HumanEval and mostly basic Python programs, achieving over 90% pass-it-one accuracy. However, it is not clear whether models actually understand these solutions, for example, with regard to appreciating the dynamic execution flow. In order to measure this understanding, we have devised the task of reproducing the execution trace of a given function call. For our experiments, we are extracting short code segments from open source repositories and competitive programming sites, as well as from the HumanEval benchmark. Paired with a corresponding function call, the language model is tasked with reproducing the list of line numbers in order of execution, which is a lightweight version of dry execution, also known as rubber ducking. The call execution can easily be verified with language-specific traces, making it simple to verify model predictions. We specifically target three research directions. The first being looking for a correlation between code generation performance and the degree to which the execution semantics of a valid solution are understood. Secondly, we compare different prompting techniques on this task, including chain of thought, direct prompting, and varying the number of given examples. Lastly, we consider the impact of code complexity as exhibited by certain concepts, including concurrency, object-oriented programming, as well as recursion. We generally estimate performance by two measures: exact match accuracy, which is binary, so either match or no match, as well as a similarity measure, which we realize through an iteratively applied Gestalt metric in order to establish a more nuanced performance estimation. As you can see, this is a continuous measure rather than a binary one. In this table, we showcase performance on reproducing traces from HumanEval solutions, using the test calls that are commonly used to validate solution candidates. We evaluate several state-of-the-art models, varying in size and performance on HumanEval. We observe that there is a weak correlation with code generation performance, with some outliers, like weaker performance in GPT and stronger performance in Gemini. Generally, models exhibit lower accuracy on this task, both micro and per class average, which we denote as accuracy hard, as compared to code generation, with those drops being especially prevalent for smaller models. We further compare chain of thought and direct prompting and observe slight improvements, mainly for smaller models. In line with code complexity, we investigate the impact of the execution trace length, so the amount of lines contained in the full execution. We find a strong negative correlation, where models across the board decrease beyond linearly in their capabilities of reproducing execution traces, with thresholds of around 25 statements for smaller models and 40 for larger ones. Chain of thought prompting can lead to slight improvements, more so in smaller models than in larger ones, but it interestingly does not help in crossing the previously mentioned thresholds. This illustration serves to showcase the most significant improvement caused by chain of thought, which occurs at mid-sized trace length, so 5 to 10 statements, and primarily concerns smaller sized models, so it excludes Gemini, GPT, and Claude, but does still have an impact on the 70 billion parameter Llama 3.1 version, which we used. Next, we investigate advanced code structures using the aforementioned concepts of object orientation, concurrency, and recursion. These sources primarily stem from open source repositories and are supplemented by manually crafted execution calls. As opposed to HumanEval, where test cases varied randomly in difficulty, we created exactly 5 test cases per source code and implemented an increasing amount of method invocations and class initializations. Note that we intentionally created this to be a more realistic execution, meaning we do not limit ourselves to a single method call. Among the advanced code concepts, concurrent code is a special case, since ordering is not deterministic over different executions of the same code. We address this by manually marking the beginning and the end of parallel processes, after which execution is joined again. These markers are then used to insert parentheses in the generated trace. During evaluation, the lines contained in the parentheses are sorted prior to comparison, allowing the model to deviate from the elicited ordering. This comes with some added difficulty, since the model has to mark the concurrent stage itself. But it is also lenient in evaluation, since not all ordered sequences are true valid options of parallel traces. Our evaluation shows that, expectedly, models struggled greatly with advanced topics. Except for Gemini on object orientation, no model can produce a micro-accuracy of over 5%. Further analysis showed that all three topics are particularly challenging due to specific factors. For object-oriented programming, models struggled with resolving nested calls and the generally increased amount of lines due to class definitions. For recursion, a main difficulty was proper backtracking once exit conditions were met and the higher overall trace length. Lastly, for concurrency, some models struggled with understanding the marking of concurrent sections and oftentimes got lost in execution due to various reasons. Chain of thought effects were mixed. Sometimes we observed the model being able to use its own output as a scratchpad, which helped during backtracking, but it also led to error propagation frequently. Overall, model ranking is similar to HumanEval experiments, but Claude surprisingly underperforms. We further investigated a small subset of traces from HumanEval and identified a number of recurring error patterns across different models in a small qualitative study. 6 out of the 9 models failed to correctly resolve a nested if condition in HumanEval problem 56, opting to skip back to the loop condition instead of advancing to the next if clause. Interestingly, the condition depth smaller than 0 was not met in this specific trace, so it is possible that some of the models intentionally pruned it. Another error by 5 models was tracing an else call in HumanEval problem 95. This is an interesting case because it is language specific, as else only serves as a marker in Python, which is never truly executed. Despite that, models listed the corresponding line in execution, which is incorrect. Lastly, there's a common error among model definitions in HumanEval problem 119. The outer definition is not called in this case, since it is assumed to be previously parsed in order to execute the given method call. However, the inner method definition is executed once in order to mark the start of its body, whereas the body itself is also not accessed prior to a relevant call. This brings us to our key takeaways. We generally observe a significantly lower performance level than on related code generation tasks, and find that trace generation still includes systemic error patterns across models as well. We believe that this work may motivate further research in the direction of fine-tuning on code execution data in order to help models learn a richer token representation for code-specific tokens, which we believe should be able to increase performance across a number of dimensions. Further, execution reasoning is still a fairly new topic, and these results hint that model performance on lower-level code understanding may be perceived as more performant than it truly is, due to strong results on pure code generation. We hope to motivate further investigation into establishing baseline performances in this direction. Lastly, some of the frequent error patterns were language specific, for instance, control flow jumps in if statements, and parsing method signature lines. Looking into cross-linguistic performances could yield interesting new results, especially concerning lower-level languages like C, which include advanced concepts like pointers or shared memory management. Given the high difficulty models are having to reproduce traces including general-purpose programming concepts in Python, this is likely going to be a very difficult future evaluation target. This concludes the presentation, and I hope to have sparked your interest in reading the full paper available here on the QR code. Please do not hesitate to contact us with any questions you may have.